what we did on Friday, just as a quick little review for us here. So want to start us off here, Andy, with number 1?
In our previous class in inverse functions, we learned that the range of f is the same as the domain of f of
Yeah, do you remember how we read this?
The negative inverse?
Almost. You got inverse right. That this means inverse. So how would you read this?
The negative.
No, this is the same as inverse. Inverse.
The inverse of the function upon. The inverse of the function.
Of the function, yeah. Right? Inverse of f.
Inverse of f.
Right.
And domain of f is the same as the range of the inverse of f.
There you go. Perfect. Okay, so it's a lot to say, but we noticed this when we looked at a bunch of ordered pairs for one function, and we noticed that if we had a series of ordered pairs in this form on our function f inverse, which is how we read that f with the superscript of -1, Andy, right? Yep. F inverse. What does it look? What would this same ordered pair look like on f inverse? No, anybody. What would? Yep. Anna, you weren't here, so maybe if you can answer, I'm even feeling better. Yx, perfect. Right. So the y's and x's interchange. Some of you said swap places. Some of you said switch places. Your book uses the term interchange places. And how this is set in this diagram is that the range, the output values of f become the input values of f inverse. The domain of f becomes the range of its inverse. So they just swap places. So we spent a lot of time Friday going over that. And then the other really big idea, if I sound like Ed Sullivan right now, really big idea, is right here. We spent some time doing this on Friday. So you want to read that first, Ryan? Okay, so remember we gave the name of this, we called this the round trip, right? Round trip. So if we start off with x and we put it into some function called g, it comes out as g of x. That output now becomes the input into our, let's make this a different color, into our f machine. And when we put it into our f machine, we're right back where we started. We have the round trip idea going on. And then the other really big idea is that it only works with inverse functions, that if we change the order of the composition, we come right back to x again. So this is one of the really special properties of inverse functions, and it's the only way that you can verify whether two functions are inverses of each other. You have to do this composition, switch the order, and hopefully you'll come back to x. If you don't, then you don't have inverses. Okay, so this is what we spent Friday doing. So today we're going to continue this idea. We're going to look at, first of all, a very simple example, but it's something that we all understand and I hope know how to do, because looking around, I think everybody, oh, except for Caitlin, she didn't come in with any socks today. So for the rest of us, I think we can do this. So I want to read this. Okay, well, I think we'll be all set. I used to do it. I used to sit up front and take off my shoes and socks and everything, but I don't think I'm going to do that. All right, so read this for us, Eliza. Okay, so my action is to put on my socks. I'm going to change you to my, and put on my shoe. All right. So how would I undo this? Someone want to help me undo it? Tell me what I would do. Caitlin? Take off my shoe and take off my sock. Okay. So there's an order implied here, an order of undoing. That's very important. So if you were to describe this, let's say someone came in who's never done any mathematics before, and you're trying to explain to them the idea of undoing when you have two actions. You got two actions here. How would you explain the order of undoing? How would you tell them how to undo it? Any guesses or from what we've written there? Yep, Anna? We have no algebra yet. All we have is the sock and shoe problem.
Whatever you do first to carry out the initial action will be your last action, and inversely for the last action, the initial conception of the action will be your first action, the reversal of the action.
Perfect. Said another way, the last thing you do is the first thing you undo. That's exactly what Anna said, but with a little more language. The first action you took is the last action you undo. So the order gets reversed. The very last thing I did, which was to put on my shoe, has to be the first thing I undo. So when you're doing inverse operations, you have to change the order. Undo the last thing, then undo the first thing, or whatever. If I had three things here, it would go, you undo the third, you undo the second, you undo the first. Okay. You have been doing this since you've been, I don't know how long, well, putting on your socks and shoes, it might be 2 or 3, I don't know. But algebraically, you've been doing this for a very long time. And so let's take a look at what we would do, how this round trip idea of getting back to where we started happens with an algebraic process. So let's do these actions. We're going to subtract 9 from x. So that's going to be my first action. I like to call this what's happened to x. Whatever your variable is, I always pick on x. So what's happened to poor old x? I've had 9 subtracted from it, so I write it this way. Now anything I do to this, I'm doing to the whole thing. So I better put that in parentheses, just in case I have to multiply it by something or divide it by something or raise it to a power. You always want to put it in parentheses. Then it says multiply the result by 5. The word result is captured right here with the parentheses. So multiply the result by 5. Okay. So if I put this in functional form, this is what it would look like. This is what my function says to do. I subtract 9 from x, and then I multiply the whole thing by 5. Now I want to undo this function, doing exactly the same thing we did with the shoe and the sock. So what's the first thing I'm going to undo? What's the first thing I'm going to undo? With the x's and the 9s. Well, what's the last thing I did here? All right, I multiplied by 5. So let's put it in words. Multiply by 5. And the first thing I did, so it's not all in symbols, is to subtract 9. Okay. So the first thing I'm going to undo here, Jesse? And how do I undo that? Divide by what? Right, divide by 5. Okay, so if I'm now finding my inverse or my undoing, I'm going to take my x and I'm going to divide it by 5. That's the first thing I'm going to do. And now the last thing I do is to undo the very first action. And how do we do that? Nick? Add 9. Okay. So voila, we have just found the inverse function for f of x. We've just done it. How do I verify this? How do I verify it? How do I know if I did everything correctly? So you, on your test Friday, you can do your own check. If I ask you to find an inverse of a function, you can do your own little check. You don't need me to grade it to see if you did the right thing. How do you verify that these two truly are, Katie? So I would compose it first, put f of x in, yeah? And then vice versa. And what do I hope to come back to? X. So let's see if we do. Okay, so let's tackle this first one. We're going to compose f of x with f inverse. So let's take a peek at f inverse. What does f inverse say to do? Take whatever input you have, divide it by 5, and add 9 to it. That's what it says to do. My input now is f of x. So I'm going to take where I see my input, I'm going to replace it with f of x. I'm going to divide it by 5, and I'm going to add 9 to it. And hopefully this brings me back to x. So let's see. What's f of x now? Oh yeah, f of x is this green thing over here. So I have 5 times x minus 9. That's my input. I divide it by 5, and I add 9 to it. Okay, so how do I simplify that? Can someone help me? Someone help me simplify that? Isabel? Isabel, do you have your hand up, or you're just playing with your hair? Whichever, okay. 5 divided by 5 gives me 1. Gives me x. I'm happy. I'm halfway home, okay? I've performed the very first part of my round trip, right? Now I got to come home. I've gone out to Hawaii. Now I got to come home. Well, I actually probably wouldn't want to come home, but okay. So how do we verify this? Someone want to tell me the process, what I would write to find f of f inverse, how I would write that. I did the first one for you. Can someone help me now with this one? Caitlin? Okay, so I take this, my inverse function, and put it in to my x in my f function. So we've got a 5 in green, and where I see x, I put the entire inverse function, which is x plus 5, x divided by 5 plus 9. That takes the place of my x. Whoops. Is that right? Do I put parentheses there? Yeah, I could put 2 parentheses. Okay. There's my x right here. This is taking the place of the x right there. And now I have to subtract 9. Okay. So I have to do 5 times this first thing. 5 times x over 5 plus 9. And then I have to do 5 times 9. I have to use my distributive property. Okay. And then I got to use my distributive property one more time. 5 times x divided by 5 plus 5 times 9 minus 5 times 9. My 5's cancel here to 1. That's my foo-foo. And I get x plus 45 minus 45, and I'm back to x. I'm relieved. I know I'm going to get my full 8 points for this question on my test because I verified that these two are inverses for all x's. Remember, we talked about checking for one value, one coordinate, an x and a y, but that only shows it for that particular point. This shows it for all x's in your domain. All right, you're going to have a chance to do this on your own in about 5 or 10 minutes, but this is the process you're going to run through. Before I move on, does anybody have any questions on how I compose these two functions? Any confusion? Okay, well, we'll find out soon if there is. All right, so start this one, Megan? Okay, so if we went back to the beginning of class 21, let's see if I can find it. Beginning of class 21, so it looks like, let's see, right here. No! There we go. All right, so here was the beginning of class 21, and we formed a bunch of ordered pairs, which were a function. We put as the input the name of the country, and the output was the female literacy rate. But when we interchanged when we interchanged the inputs and outputs here, we realized we did not get a function. We only got a relation because 99 went to Germany, and then 99 was also associated with Japan. And we know that for every input, we can have one and only one output. So this is called a relation. It was not a function. So that's what we're referring to as a recall in this on this page right here. All right, so let's see if I can find where we were. Oh no, that's our activity for today. Let's see. Here we are. Okay. So that's what we're referring to here, that when we swapped the inputs and outputs with the female literacy in the country, we did not end up with a function. So is there a way, that's what we want to figure out now, is there a way to look at a graph of a function and tell whether or not it's going to have an inverse? So notice I have a linear function and a quadratic function. So red here represents my linear function, so I'm just going to take this line and make it red. And these purple writing here represents my parabola x, x minus 1. Okay, and just a little review of all the transformation work we did. You can see that the parabola of the quantity x minus 1 squared is shifted to the right 1 unit, from the transformation work we did. Okay. So let's take a look. Here's 4 points that lie on this straight line. Those 4 points are also called solutions to this equation. If you pick any of these points and you throw it into this equation, the left side equals the right side. So according to the work we did on Friday, if we wanted to start to look at whether this red line here has an inverse, we could start playing with these interchangeable coordinates here. And we see here that for each x value, we have one and only one y value. Let's see if that holds true for our parabola. So we would say this straight line has an inverse. Right? Let's take a look at the parabola. For each input here, do we have one and only one output? Why not, Will? You're correct. So what is it that you see here that leads us into problems? We're looking at this one, right? And you said no right away. You were, oh, you didn't? Who said no? Oh, Andy. Oh, okay. Andy, want to tell me what? Sorry, Will, I thought you said no. What?
Sure, there are two ordered pairs that have the same x value for -1.
Right, so after we interchange our x and y, we see, just like with the nations and the female literacy rate, that we have the same x value going to two different y values. What does that look like on our original function? On our original function, we had two different x values. We had -1 gave us 4, and 3 also gave us 4 on our original function. So we had two x values that were different. This x value does not equal that x value. However, it brought you to exactly the same output. And that's fine. That doesn't violate, this is still a function. But when you swap it, you now have that same output becomes the same input, but now our x values are different. That's going to be a problem. So we say that this parabola does not have an inverse function as it is currently written over its whole domain from -infinity to infinity. So let's see if we can find some way to visually do this so that we don't have to go through all of this stuff. Is there some way to visually do this? Okay, Jesse, want to read this for us? So that's the question. Can we look at its graph and tell whether we have an inverse? So let's start. I'll show you this series of steps we go through. You want to draw a horizontal line through y equals 4. Does anybody, let's go back to, you don't have to go back, I have to go back. Does anybody know why I picked the line y equals 4? Isabel? Both functions have that point, yeah? And why did I decide that? Why did I pick that as maybe a place to start? Can anybody, yeah, Caitlin? It's a perfect square, so it's easy to find on our graph, right? Okay, and I'm still looking for something else, but maybe it's too hard a question, so we'll come back here. So draw the horizontal line, y equals 4. You have rulers in your little toolkits there you can pull out. You can use your studio bookmarks. I'm going to use my index card here, and I'm going to draw a horizontal line right through y equals 4. So you do the same at your seats. Okay. Well, mine came out a little bit higher than I wanted it to, but that's okay. It's a little bit higher on the right side. So there's my line, y equals 4. Now, if I'm just looking at my linear function, so try to ignore the parabola. If I look at my linear function, how many times does this line y equal 4 intersect with my linear function? Once, right? At 3, 4. In fact, if I take any horizontal line, and I'm coming right down from top to bottom, how many times is that horizontal line going to intersect that linear function? Once. And that's because this function is always increasing. So when you change your x value, you get a different y value. You'll never get exactly the same y value like you do on a parabola. It's always increasing. Similarly, if I take this line and just change its slope, it's always going to be decreasing. So any graph of a function that's always increasing or always decreasing, boom, it's automatically only going to have, for different inputs, different outputs. So it will pass this test, which we're calling the horizontal line test. If you can put any horizontal line through your graph and it touches it at one and only one spot, voila, you know you've got an inverse. You don't have to go through all this other crazy stuff we've been doing. Okay, so that's a nice visual. All right, now let's focus on the parabola. So let me make that kind of grayish purple again. And now where is my blue line y equal 4? How many places is it crossing my parabola? Twice. And it was the points that Andy pointed out, the -1, 4, and the 3, 4. So that's why I picked y equals 4, because we had identified that earlier as a problematic spot. All right, so this is what we refer to as our visual test for whether a horizontal line has a function or not. And we just say, if there is no horizontal line that intersects the graph of a function at more than one output, we're golden. We have an inverse function. Okay. So this kind of seems like I'm beating the horse here, because we're going to keep going with this idea. So at your seats, I think it took my last class about 10 seconds to do this, but at your seats, do the usual. Discuss this problem with your table mates, and when you're done, put up the flags, and I'll know how each table is ready to go before we move on. Okay, so what did we get for the first one? Does it have an inverse? No. In fact, this even is worse than the one we looked at, right? Because if we put a horizontal line through this, we can pick a zillion horizontal lines, but even if we put one through, we hit it in 3 spots, right? So this definitely violates the horizontal line test, so this does not have a function, no. And this function is always increasing over its domain, just like the straight line. And what did you say for this? Does it have an inverse? Yeah, absolutely. It only hits it in one spot. So I asked my first class, and we haven't gotten here yet, but if I asked you what the equation for the very first graph might look like, what do you think would be the highest power of the function? that's plotted here? What would be the highest power you'd see on any x? 3. Now you said that 3 with a little bit of a question mark. Who said 3? Isabel. So you're right. You're right. And what kind of led you to thinking it might be 3? It changes direction twice. That's great. That's one way of seeing it. Anybody else have another way that they might see that this is a function to the third power? Well,
Because it goes down, or yeah, it goes down.
right. That's the changing of direction. It's just another way to look at it. Okay. Jesse? Through 3 times. When you say through 3, right, so that tells us about the fact that it doesn't have an inverse. So the fact that it goes through 3 times might be another idea that it has 3. Okay. Well, does anybody know? Let's take a look at this function. Does anybody know what might be the highest power on this function? We haven't done this yet. Does anybody know what that might be? Anna? Okay, if it was a square, it'd have to look like a parabola, right? It'd either have to be a happy parabola or a sad parabola. And that doesn't look like a parabola. If it was an x, it'd have to be a straight line. It's cubed again. It's just like x cubed, but it's got some kind of either stretching or shrinking or stretching or some transformation going on. But look at the difference between these two x cubes. This one has a valley and a mountaintop. This one is always increasing. So the difference is this one would have be something like, I'm not telling you exactly what it is because I don't know what these points are right here, but this would be something like negative 2x cubed plus 5x plus minus 1. It would have 3 terms. This one only has 1 term. Okay, so that's just a little peek into the future. Next week we're going to do polynomial functions, and this is the type of thing we're going to be noticing. The other idea I wanted you to know is how many x-intercepts does it have? 3. It has 3 x-intercepts, which means let's just call this point x1, this point x2, and this point x3. So if we were trying to find those, we would factor our polynomial and we would set it equal to 0. We would have 3 different factors. 3 different factors. And therefore, if I multiply this out, I'd have to get an x cubed. So that's another way of seeing that this is an x cubed because you have 3 x-intercepts. Okay, but the changing of direction and the 3 x-intercepts, it's a little bit off subject, but you actually know a lot more than you even know you do. And so I wanted to point that out here with the x cubed. All right, so another way to say this whole thing we've been doing is if you have 2 different inputs, you must get 2 different outputs in order for a function to be past the horizontal line test. And another name we give all of this is that if a function passes the horizontal line test, we say the function is 1-to-1. And therefore, every 1-to-1 function has an inverse. Okay. Yep, Anna? No, that wouldn't be okay, because let's take a look at that. So thanks for asking that. So let's take 2 x's that are different. Like how about -1 and 3, since we just looked at those a minute ago. Back here. Here we got 2 different x's, right? Here's x1 and here's, so we can't say the x's, we can say the x's are different, but in this case, the y values are not different. 4 equals 4. So it fails this. If we're going to have 2 different x's, we must get 2 different y values, or else we're going to run into that same problem when we take those y values and interchange them. Okay. Any other questions? Sometimes things that are very easy to do when we write them symbolically and with math so that we can explain it for any situation, it makes it look hard, but that's all it's saying. That's all it's saying is the picture we just looked at. Our x1 and x2 were different on the quadratic. Our y values, our outputs were not different, so it wasn't 1 to 1. But when we looked on our line, since it's always increasing for different x values, our y values were totally different. All right, so let's play the game where we algebraically find the inverse of a function. We've looked at coordinates and we found the inverses by swapping the y's and x's. We've looked at graphs and how to determine if it has an inverse. Now let's actually find algebraically the inverse. And you've done this over and over again. So keep this function in mind, and I'm just going to scoot down here. You have it on your sheet, and let's just play the game that we did with the socks and the shoes. Tell me in our function, oh, actually, I'll write it up here. What was it? F of x equals 5x minus 6. Is that it? Okay. So what's happened to x? If you were evaluating this for a value of x, what's happened to x? Tell me what's happened to x. You put a number in for x. What's the first thing you're going to do? Multiply by what? Okay, thank you. Multiply by 5. And then I only have 2 things happening to x here. I wish I had a problem with 3 things or 4 things. And what's the last thing that's happening to this? Subtract 6. Okay, so we know this game. Now we're going to undo everything that happened to x, everything that happened to x. So let's undo it. So we start with the last thing we did, and that becomes the first thing we undo. So how do we undo subtracting 6? Add the inverse operation, add 6. So here's x. Now I'm going to add 6 to it. And then the last thing I do is to what? Divide by. Oh, you guys are really sleepy today. All right. This is my inverse function. I didn't even have to do any fancy algebra or follow any set of steps that the book gives me. Okay. We can do all of these really by looking at what's happened to x and then undoing each of those in this order. But, that could take a while. So let's go see how we do this with the algebra. Your book calls this the switch and solve strategy. I always think of some kind of spy thing or something when I see this switch and solve. So the first thing it says to do is to replace f of x with y. So I'm going to take this function and I'm going to put it into my usual xy notation. So y equals 5x minus 6. And since we know that our inverse function interchanges x and y, let's interchange it right now. So where I see a y, I have an x. And where I see an x, I have a y. And now to undo this equation, to undo everything, I want to get back to y. I want to come back to y equals. So let's see. The first thing I undo here, if I'm solving this for y, is I'm going to add 6 to both sides. So I get x plus 6 equals 5y. And then the last thing I undo is the multiplication by 5, which is to divide both sides by 5. So I get x plus 6 over 5 is equal to y, which is what we just got. And now just to put it back into my functional notation, I know that x plus 6 divided by 5 is f inverse. And how do I write f inverse, Andy? Negative 1. All right. Okay, so we're done. There it is. That's our inverse. So now at your seats, I'd like you to spend a few minutes together and check with each other. I want you to verify that f of x and f inverse that we've just come up with truly are inverses of each other by performing these 2 compositions to see if you come back to x. Our inverses, I've checked everybody, but we have some different answers here on number 8. So let's take a look at number 8. These are the 2 answers that I've seen, okay? I've seen this, f of inverse of x. I've seen this answer is the cubed root of x, and the negative 1's on the outside of the subtraction of 1. And I've seen this, where x minus 1 is inside. Okay? So let's take a look at the verbal description of what's happened to x over there on the sideboard. So if I asked you what's happened to x here, you would say, I've cubed it and I've added 1 to it. So to undo it, you start with your x. To undo it, the first thing you do is you subtract 1 from x. Again, just like in the very first one we looked at, you want to put that in parentheses. Now to this expression, x minus 1, you apply the cubed root. So this is the inverse function of x cubed plus 1. It's the cubed root of the entire thing called x minus 1. So I think what some people are doing are they're doing this in their mind, and you're going like this. In your mind, I think you're going like this. I think that's what you might be doing. Nope, that's not what you're doing either, because that doesn't give you this one. So I think the only way of explaining why the 1 is on the inside versus the outside is, well, we could do it with numbers, or we could verify it with the property we just looked at. But remember, the very first thing we do is we subtract 1 from x. So that is a result. And just like with the very first problem we looked at, whenever you add or subtract something from x, you have to see that as a single quantity or number. So put it in parentheses, that will help you. So for the very next thing you do, you apply it to the entire quantity, which is to cube root it. That's usually the only mistake at this point that students make. So if you happen to have this, it's fine. It's a very common mistake. Just write a little note to yourself about how to undo the error you just made. And that will help you for later on when you're doing some homework. Okay, I've got 4 minutes left here, and we've got a lot to do because I want to give you 20 whole good minutes to work. I want to show you how you sketch the graph of an inverse function. If you have the graph of your function f and you want to sketch its inverse, there's a wonderful series of steps you could do. You can also use a reflection idea. You can use these little red mirrors and you can reflect. We talk about reflecting over the y-axis and reflecting over the x-axis. Those are the languages we use for transformation. Now we're going to talk about reflecting over the line y equals x. And when you have to sketch these inverses in a few minutes, the first thing you're going to do is draw the line y equals x, which is a very easy line to draw right through the origin with a slope of 1. And then you're going to place this thing right on that line, and you're going to look through it. And when you look through it, you're going to see a beautiful reflected image of your inverse function. So I want you to do this 2 ways today. I'm going to show you how you do it by plotting points. And in fact, if some of you came up here right now and looked, you would see it. I guarantee it. Someone want to come up and take a look? Come on up here, Evan. Come up here. You're taller than I am. I got this right on here. Look through there. Come over here and look right through there. Can you see what's happening?
Yeah, it's.
And then as I'm,
reflecting,
yeah,
It's going.
yeah, yeah.
Oh,
Not
it's
cool?
going. Yeah, that's perfect.
So if you were here looking through that reflection, this is what you would see. Just like that. Okay, that's what you would see. And what you should notice is that if you drew a line from the point on your function f to its corresponding point on f inverse, the distance on either side of that line y equals x is the same. They're congruent. The distances are congruent. Now, some people have the ability, it's not one of my talents. I know I have a lot of talents. This is not one of them. Some people can look at this graph of f and they know they have to reflect it over this line, and boom, they can draw it. It's amazing to me. As complicated as these graphs can look, they can do that. I have to, I mean, I'm better than I was like 30 years ago because I've been doing it for a while. But, you know, one way to do it, if you don't have that ability and you don't have one of these handy, is you pick a couple of nice points on your original graph. For example, On my original graph, I have my y-intercept 0, 1. I have the point 1, 2. I have the point 2, 4. And I have the point 3, is it 3, 8? 3, 8. And then you can do the interchanging idea. On your inverse, this now becomes 1, 0. So look, your y-intercept becomes your x-intercept. 2, 1, 2 becomes 2, 1. So then you just plot each of those points. 3, 8 becomes 8, 3. Oh, I'm off a little bit. Okay, and then you just sketch it. We're looking for sketches, not accuracy. And then if you get a really funky looking one, like a piecewise function like this, you do the same thing. I'm going to draw in my line. What did I do with my card? Okay, I'm going to draw in my line y equals x. Right through here, y equals x. Y equals x. Okay, here's my line y equals x. Some of you right now, I know you have the ability to look at this and see your inverse function. You think about reflecting that over the line. I'd have to cheat and go like this in order to see it, but I see it. Or you can say, pick some nice points on here. They're already illustrated for you. -3, -2, -1, 0, and 4, 2, and interchange the coordinates. -2, -3, 0, -1, and 2, 4. And now, once you do that, -2, -3 is right there. 0, -1 is right here. And 2, 4 is right here. You can now connect these, and you have your inverse function. And you can see that this is a mirror image of f, but the mirror is placed at the line y equals x. It's an interesting thing to think about for those of you who are more mathematically inclined as to why we use the line y equals x. That reflects your invert, that swap coordinates, for those of you who'd like to think about something different. Okay, you have a bunch of activities. Make sure when you do these, sketching these graphs for the inverse, you do some by picking and plotting points and some by reflecting over a line with the mirrors. You have rulers and these little mirrors at your seats. Any questions, let me know and I'll help you out. We had one more problem to do. I'll do that on Wednesday. I want you to have time to work at your seats now.